Okay, I'm gonna go over the bell ringer here. I pulled up a not as nice version that I can write on up here. All right, so key to doing this problem is again that we're asked to put the answer in hertz, and again hertz is another way of saying hertz is inverse seconds. So it's per second. How many times does something happen per second? All right, so the problem is our time here is 4 days. So we can figure out how many times it flashes per day easily. We just do that divided by 4, but we don't want per day. We want to figure out how many times per second. So if I had, basically I want to convert 4 days into seconds. So off to the side here, I'm going to do the dimensional analysis just so you see it. Okay, when you do dimensional analysis, the thing I want to cancel goes on the bottom, right? So again, I'm multiplying by a fraction, right? And I don't want days. I would like seconds, right? That's what ultimately I'm trying to get to, seconds. So instead of days, I want to get rid of days. So in order to get rid of days, right, since this is a fraction, I'm going to multiply by another fraction we call a conversion factor. If I want to get rid of days, it has to go on the bottom, right? Because when I multiply, there'll be days in the top and a days in the bottom that will cancel. So if I want to get rid of something, it's got to go in opposite place. And I'm going to go from days to, again, if you happen to know how many seconds are in a day, you could go there immediately. I don't know that, so I know how many hours are in a day. So 1 day, 24 hours. Now look what will happen when I multiply this together. The days will cancel, and I would just have hours left. So if I want to know how many hours, I'd be done, but I don't want hours. So I'm going to go from hours to minutes. Sorry, my pen is not great. Okay, hours to minutes. So again, hours would cancel. I would have minutes. 1 hour, 60 minutes, of course. If I wanted minutes, I'd be done, but I don't want minutes, I want seconds. So one more time, I want to get rid of minutes. So it has to go in the opposite place. In this case, it's the bottom. And I'm going to go from minutes to seconds. And again, I know 1 minute is 60 seconds. So now the only unit left here is seconds. That's how I know I've done this correctly. So I'm just going to do the math here. So I'm going to multiply across the top. So that's 4 times 24 times 60 times 60. All right, and I get on top here 345,600 seconds. On the bottom, technically I have to multiply across the bottom as well, but it's just 1, right? So it's not going to matter because anything divided by 1 is itself. So then to find the frequency in hertz is going to be the number of times the event occurs, which is 28,480 times, divided by 345,600 seconds. Put in my calculator. I got 0.08. I'll just round it to that. Hertz. So this is not actually occurring very often. In fact, you can tell. I just kind of made up a number. I just took a guess, and my guess is pretty low. I was trying to look maybe for like 2 or 3 hertz, but anyways, didn't quite get there. So actually, pretty low frequency, relatively speaking. But that would be the correct answer. Okay. Don't forget to put that into your bell ringer document. And again, I'll try to remind you tomorrow just to submit that since we'll be done after that. All right, so today we're going to talk about the electromagnetic waves and electromagnetic spectrum. This is a pretty big concept for what we will be doing. So again, it's just important that we go over this in some detail. All right, so the biggest thing that's different about electromagnetic waves is that they do not require a medium to travel. And I should mention, when I say electromagnetic waves, you should hear light. That's what I'm talking about. I'm talking about light. Light does not require a medium. It can travel through empty space. For a long time, people thought that it couldn't. People thought there was this thing called the aether, A-E-T-H-E-R, that was just this sort of this stuff that permeated the entire universe that allowed light to travel. Because, I mean, people knew at some point that there was no air in space, there was nothing in space, it was a vacuum, but they still knew that light obviously travels through space. So there was a famous experiment called the Michelson-Morley experiment, which tried to see the properties of this ether, and what they determined was that it didn't exist. And so that's a big conclusion. But electromagnetic waves do not require a medium. We're going to talk about why in just a moment. Okay, so to see why, there's a video I'll show you, but I'm going to do a quick demonstration first. So this video here just kind of shows a quick demonstration that's, I think, pretty good.
I have a pipe. Yeah. Do you want to hold it? Do you know what it's made of?
Metal? Is it brass?
Copper.
Is copper magnetic?
No.
Uh-oh.
I'm going to go no. I didn't think it was.
I'm going to go yes.
Yeah.
Well, why don't we check? This is a magnet, and I'd like you to use it to test whether the copper is magnetic.
No.
I want you to be 100% sure here. What do you think?
No.
It's not magnetic.
I said so.
Okay. Is there anything in there?
No.
What do you see in there?
That's nothing.
So why don't we drop something through it and just make sure it's empty, right? Okay, this is not a magnet. So this isn't a magnet, but let's see what happens when we drop it through. That was a dull experiment, wasn't it?
Yeah.
Okay, so what's gonna happen if we drop this magnet down the pipe? It's gonna pull through. Let's do it. 3, 2, 1.
That was weird.
That's well cool.
Took longer.
What's slowing the magnet down?
It's got to be magnetic poles or something. I don't know. North, south.
Something to do with the polarity of the north and the south poles.
But it doesn't stick.
But then it's not magnetic, so it shouldn't do anything.
Right, you guys saw that.
That is slightly magnetic on the inside somehow.
It's going to be magnetic inside, isn't it, or something? Does it like...
Kind of tilts. I think it's the powers of the universe.
I don't know why it's doing it.
Well, this is what's exciting, is only a few blocks from here was the lab of a guy called Faraday.
In October 1831, he built the world's first electric generator here, a magnet which you push and pull in a coil to generate electric current.
So that's the actual...
Yeah, the world's first electric generator.
And there's a permanent magnet in the middle?
There's a permanent magnet, yeah.
It was Faraday who realized that it's a changing magnetic field that actually can generate electric current. So as the magnet is falling through the pipe, it's creating a changing magnetic field that generates little electric currents, so-called eddy currents in the pipe, and they create an opposing magnetic force on the magnet, slowing it down. So it actually turns the pipe into an electromagnet,
I see.
which pushes the magnet up. And this is what's known as electromagnetic induction. So it causes my LED to light up there. But it's important that you move the magnet quickly, because if you move it too slowly, the magnetic field is not changing fast enough to generate enough voltage to light this LED. This is actually the way all electricity is generated.
Is it?
Yeah, you move a magnet near a conductor and it creates electric current. But where is this electrical energy coming from? You can't get energy for nothing. Well, Faraday realized that there must be a force pushing back on the magnet. It's the same force that slows this magnet down as it falls through the pipe. So there's actually energy being converted from gravitational potential energy into electrical energy and eventually to heat. So this pipe is warming up by taking some of the energy out of the falling magnet. Is that any good or what?
Oh, it's very good.
This way, and these currents coming around this way.
Okay, so yeah, so basically this is how an electric field works, because a changing magnetic field, so you see a changing magnetic field creates, sorry, the magnetic field is blue, creates a changing electric field. And they're 90 degrees from each other, which doesn't matter too much, but it propagates in 90 degrees. So as this magnetic field gets larger, so does the electric field. And so because they produce each other, it's what we call self-propagation. So the electric field just moves on, or the I guess I'd say the wave moves without a medium because it doesn't need one because it creates itself. Okay, so again, that sums it up. When electric field changes, so does a magnetic field. Changing magnetic field causes an electric field to change. When one field vibrates, so does the other. And so you end up with this wave that can travel without any medium, and it travels forever. It just keeps on going forever and ever, which is going to be incredibly important as we try to figure out and try to answer questions about things beyond Earth, right? Because again, electromagnetic waves are what can travel to us. Because they can travel through a vacuum, they can travel all the way from whatever distant place they originate to us. They move very quickly, right? So it's about 300,000 kilometers per second. That's the speed of light. So that is an incredibly fast speed. In fact, as far as we know, physics says that this is the fastest speed that is possible. Nothing can travel faster than this for various reasons. One of the biggest scientists who was able to show that was Albert Einstein, right? So when he talked about relativity, that has a lot to do with this speed of light and the fact that everyone would agree on the speed of light and the fact that it's unchangeable. So the speed of light is set. Light can't go faster, light can't go slower, and every time we measure it, no matter who is measuring it, no matter where they're measuring it from, they will get the same constant. In fact, it's so constant that usually when we represent the speed of light, we symbolize it with the letter C, because it's always the same. Now, this is incredibly fast, right? So at this speed, right, imagine that a light only travels in straight lines typically. It can be bent through something called refraction, but we're not worried about that right now. But the point is, light travels very quickly, 300,000 kilometers per second. That's fast enough that if you were, could go in a circle, that would go around the world 8 times in 1 second. That is unbelievably fast. That is, none of us can understand how quick that is. And the great irony is that even though that's very fast, it's actually slow on a like cosmic scale. I'll put it to you this way: if you were to travel that speed, so again, think about going around the world 8 times in 1 second. Again, unimaginably fast. If you were to travel at that speed, to get to the nearest star, that's not our sun, of course, to get to our sun, okay, let's talk about that. To get to the sun, it would take 8 minutes traveling at that speed. This unimaginably fast speed still take you 8 whole minutes to get there. To get to the next nearest star, it would take you 4.3 years traveling at the speed of light. The fastest speed that we know of to get to the next nearest star would take 4.3 years just to get there. To get there and back, that's 8.6 years. It is incredibly slow on the scale of the universe. To get to the nearest galaxy, we're talking, I think it's 800,000 years. So, yeah, the speed of light is very fast, but the universe is very big. And so, because the speed of light is finite, what we'll discuss is when we look out into the sky, and when you see light coming to us from distant places, we're not only looking at that light, but that we're looking at that light as it was billions or millions of years ago. Okay, we're going to talk, I think, more about this, tomorrow. But I just want to point out that a light has properties of waves and particles at the same time. Okay, so we're going to talk about 2 experiments tomorrow. One is called the double slit experiment, and one's called the photoelectric effect. Both experiments show light behaving in one specific way. So the photoelectric effect shows light definitively behaves like a particle. The double slit experiment shows that light definitively behaves like a wave. And it does both of those at the same time. So it's quite complex. But like I said, I think we're going to discuss that tomorrow. So here's the electromagnetic spectrum. So the electromagnetic spectrum is the range of electromagnetic waves when placed in order of increasing frequency. So as the frequency gets higher, right? So we start down here in radio waves. Okay, so radio waves are down here. those are the lowest frequency. Now remember, there's a relationship between frequency and wavelength. The longer the frequency, I guess I should rephrase that, sorry. The higher the frequency, the shorter the wavelength. The lower the frequency, the longer the wavelength. So when you look at the electromagnetic spectrum, you're also organizing them, when you organize them from lowest to highest frequency, left to right, you're also organizing them by wavelength, from longest wavelength to shortest wavelength. Okay, so these are the different types. We're going to go over kind of specifics, but radio wave is the lowest, microwave is above that, infrared, visible light, right? And this is what when you think of light, you no doubt think of this. You probably think of a light bulb or some kind of, something that's bright, right? That's only visible light. That's one incredibly small portion of all of this. We cannot see any of this stuff down below. You cannot see radio waves. You cannot see microwaves. You cannot see infrared rays. Likewise, you cannot see anything above this. You cannot see ultraviolet. You cannot see X-rays, and you cannot see gamma rays. They are all around us all the time. I mean, hopefully these ones up here are around us less, right? Earth has some protective measures like the ozone to keep some of these really harmful rays out that come to us from the sun. So hopefully these are less, but these are used all the time, as you'll see in just a minute. I mean, right now, just the fact that that there's Wi-Fi around you, that there's internet, there are phones. I mean, all of these devices are going to use radio and microwaves. So there are waves everywhere around us, but there's only a small sliver we can see that is visible light. Okay, so again, the wavelength goes from long to short. This also has to do with energy, right? The amount of energy in a wave is related to frequency. A higher frequency wave has more energy than a lower frequency wave, which is why these waves up here can be dangerous. Now, they can be used in productive ways, but they can also be dangerous because they have a lot of energy associated with them. Okay, so again, just the electromagnetic spectrum here. Again, the energy goes up, as you can see, from left to right. The frequency goes up from left to right. The wavelength gets smaller from left to right. It gets smaller as you go up. And you can see some pictures about like how big these things are, these waves are. Okay, so let's start with radio. Longest wavelengths and lowest frequency of all the electromagnetic waves. So you see they're quite large on the scale of buildings to humans. And really, no, there's no lower limit. I mean, I guess technically the longest wavelength would be the size of the universe or something, but there's basically no limit to how big these waves can be, how long the wavelengths are. Okay, I'm going to show you a quick video here on cell phones because, again, they're obviously all around us and how they work using some of these waves. So if you're watching this video later, you can watch it yourself. I'm just going to pause it here. But even though it's complex, the basic idea is simple, but it's layered on to complexity. So so the basic idea is, when I send a message, my phone has an antenna. So it's taking an electric signal that antenna vibrates in a specific way. It emits an electromagnetic wave, a radio wave. That radio wave goes out in all directions until it reaches a cell phone tower. Then that cell phone tower receives that same message, those same waves, converts it back to an electric signal, and then that electric signal is sent through cables to whichever cell tower is closest to whoever you're trying to send a message to. And the fact that the speed of light is so fast means that all this happens instantaneously. And it is, I know we sort of inundated to it, but it is magic. It is basically magic and wizardry in a way that we can send messages instantaneously over any distance on Earth is amazing. Okay, radio is also used in GPS systems, which obviously triangulate your location. So the way a GPS works is if I'm on Earth, I usually should be in view of about 3 of these satellites. Now, these satellites are in what's called geostationary orbit, so they sit exactly in the same place. So basically, we know Earth spins. Those satellites spin at the exact same rate, so they're always over the exact same place. So when I am, if I'm down here in Mexico, then I should have my signal will go out and should hopefully hit at least 2 or 3 different satellites. And if we have 2 or 3 different points, hopefully 3, we can triangulate my exact location and to determine where I am. Obviously, with radio waves, you're probably going to think about the radio. And of course, the radio, if you're using traditional radio, does use radio waves. Now, if you're using something like satellite radio, I think those might be actually microwaves. But again, it's a pretty small distinction. MRI, another use of radio waves. They use short, higher energy radio waves along with magnet to create an image of the inside of someone's brain, which is pretty useful. Okay, going up next. Next category we have are microwaves. Okay, these have a shorter wavelength and a higher frequency than radio waves. We're looking at about the centimeter length. Okay, so if you're talking about centimeters, that's typically a microwave. Obviously, you probably think of a microwave oven, and sure enough, that does use microwaves, of course. The way they work is the waves are messing with the water molecules in your food. I mean, all food has water in it, basically. And those water molecules end up getting spun around, and as they spin, they generate a lot of heat and a lot of friction, which heats up your food from kind of the inside. These are also used in radar guns. So radar actually stands for radio detection and ranging. So again, if you get pulled over by a police officer as you start to drive and you were going too fast, the way they know you're going fast is because they use a radar gun. Specifically, as we previously discussed, they can use radar along with the Doppler effect to determine your speed. Up next, we have infrared. By the way, that prefix infra means below. So this is below red. Now, the way they were actually discovered was, you probably know that one of the first person to use a prism to break up visible light was Isaac Newton. He took white light, passed it through a prism, and he got the rainbow, the spectrum that we see of visible light. He wondered if there was anything to the left of the red light. So what he did was he took a thermometer and he put it just to the right, just to the left, I should say, of red. And sure enough, he detected there was extra heat there. And he determined that there must be some kind of wave that's there that we're not able to see. And so infra means below, infrared means below red. Infrared is most commonly associated with heat. Okay, we are objects that have a temperature, and we'll eventually talk about this when we talk about radiation due to heat. But you are radiating energy all the time, heat energy all the time. Specifically, the frequency of light that you're radiating is infrared. Okay, you are a light bulb, right? But it's not light that we can see. It's light that's below what we can normally see. So I can't see the light that you're radiating with my eyes. However, I can use different tools to see it, such as infrared cameras. So this is called a thermogram. It just looks at infrared waves and detects that and makes a map of the heat that's there. And so you can take these infrared cameras and you're able to see temperatures very specifically. In fact, every day when you come to school right now, you get your temperature taken, and that's what it does, right? The way that these thermometers work is they look at they measure the infrared energy coming off of you and determine your temperature based on the frequency of that energy or the wavelength of that energy. I'll show you a few quick videos again. If you're watching if you're recording, you can watch these on your own. Okay, so visible light is what we are most familiar with. It's what we see all the time. You're currently seeing visible light. Everything you see, whether you're here looking at the screen in the front or you're looking at a screen on a computer, all of this is visible light. So this is what we can see. And again, it follows this pattern of a visible spectrum where we have the lowest frequency, or the longest wavelength is red, and then the shortest wavelength is purple, although really we'll usually call it blue. Okay, so again, going on, ultraviolet UV rays. They carry more energy, right? So when you think of ultraviolet, we have many uses for it. We can use it to kill bacteria and sanitize equipment. We can use it to protect against the sun. There's some pretty gross pictures here, so you don't have to look if you don't want to. But basically, sun damage is caused by UV rays that come into us from the atmosphere. It does have useful benefits, right? Because it does encourage the production of vitamin D, which is obviously important for us. So if you go out in the sun, that produces that. Moving on, we have X-rays. Shorter wavelength, higher frequency. They carry more energy. They can penetrate more matter, right? And so X-rays are obviously used in taking X-rays. The reason why these work is because there's a film behind you. There are X-rays shot at the subject. In this case, it's a bat. Some X-rays are absorbed. For example, where the bones are, right? The bones have a higher density. They absorb the X-rays. So this part is, is there. Doesn't receive as many X-rays, so the film shows it as light, and then places where X-rays get to, it shows as exposed as darker areas. And obviously, this is used in medical practice to see if there's been a fracture of bones or something like that. Too much exposure. From here on, as you get too much exposure, this is called ionizing radiation. It can eventually cause cancer. It can damage your cells and damage them in ways that they start to replicate. This is why whenever you go to the dentist, they put that really heavy vest on you when you get your teeth X-rayed. Now, is it dangerous? No, but it's still good to take precautions. And X-ray technicians, you'll notice that they don't stand next to you. They're pretty far away because they are the ones who would be at risk of getting too much exposure since they do that every day. That's why they stand so far away, because, hey, they don't want to get, obviously, too much exposure. You can use it to check for cracks. You can see here a crack in a foundation. And finally, the highest is called gamma rays. So gamma rays have the most energy. They have the highest frequency. And there is really no limit. Notice these waves are incredibly short. We're talking about nanowaves, nanometers, I should say. But there's really no upper limit. There is an upper limit, but it's extremely high upper limit to the length that these rays, how short they can be. These are incredibly powerful, have the highest. They are used in certain radiation treatment to kill cancer cells. Right, so they usually have a beam of energy, and they have to focus it at a very specific area. And what it does is it destroys cells, which is a good thing if you're trying to destroy cells that are bad for you, like cancer cells. But it can be incredibly dangerous, which is why you have to use very specialized equipment there. They can also turn you into the Incredible Hulk, I guess. That's at least his origin story. When there is a nuclear explosion, these emit gamma rays. And I didn't put this in here, but there's also this concept called a gamma ray burst. At any point, a star could go supernova, and when it does this, it creates what's called a gamma ray burst. So it's very, very intense gamma rays that are in a very small cone. But if they were to hit Earth, they would pretty much wipe out our atmosphere and kill us, and there's nothing we can do about it other than hope it doesn't happen. Mathematically, it's a pretty small chance, but again, there's not a thing we can do about it if it were to occur. The brief summary here: all electromagnetic waves travel at the same speed. They have different wavelengths and frequencies, and we put them in the spectrum where we organize them from longest wavelength to shortest. Also the same of lowest energy to higher energy. Okay, so again, when we think about light, we think about this little tiny patch right here. But the electromagnetic spectrum is so much more than that. And again, it is used, literally, it is used in everything that we do. It is pervasive.